Bismillahirrahmanirrahim. In this lecture, we are going to study the equivalent circuit of synchronous generator. In the previous lecture, we studied the induced voltage EA. The voltage EA is the internal generated voltage and produced in one phase of a synchronous generator. However, the important thing is that this voltage EA is not usually the voltage that appears at the terminals of the generator. So the voltage appears at the terminals of the generators is different than the voltage induced in the stator winding. Why? We will study in this lecture. Why is the output voltage V phase is not equal to EA, and what is the relationship between the two voltages? The answer of these two questions we will study in this lecture, and then we will drive the equivalent circuit model of the synchronous generator. Why V phase is not equal to EA? There are number of factors. Which factor? The first one is the armature reaction. What is the armature reaction? We will study later in next slide deeply. Here, the distortion of the air gap magnetic field by the current flowing in the stator called armature reaction. Second factor is self-inductance or reactance of the armature coil, also the resistance of the armature coil, and the fourth one, the effect of salient pole rotor shapes. As salient pole rotors poles are sticking out shape, and it also produce some distortion, so which also produce some effects due to which V phase is not equal to EA. So we will study these factors in the next slides one by one. The first three factors are important, and we will study these three vectors and then drive a machine model from them. The effect of salient pole is not too much important because it produces a relatively minor error. The errors produced by this are relatively minor, so this can be ignored for the simplicity. So the first factor is the armature reaction. What is the armature reaction? When a synchronous generator rotor is rotating, a voltage EA is induced in the generator stator winding. Okay, this is simple. If a load is attached to the terminals of the generator, then a current flows, and this current produces its own magnetic field, which is denoted by BS. This stator magnetic field distorts the original rotor magnetic field and then produce the another magnetic, which is the B net, as we already study and know about that B net is the resultant sum vector of the BR and BS. Because of this effect and the distortion of the original rotor magnetic field is called armature reaction, because the armature stator current affects the magnetic field. So now this figure shows a two-pole rotor spinning inside a three-phase stator. This is the two-pole rotor and this is the stator. Okay, I'm going to draw it here. This is the stator. And this is the rotor. The rotor magnetic field BR produces an internal generated voltage EA in the stator winding, whose peak value coincides with the direction of BR. If BR direction is this, BR, then the same ER direction is the peak value of ER occurs at this point. EA induced maximum, and rotor is spinning in this way, omega m. In this condition, with no load to the generator, if generator is connected, no load is connected towards the generator stator winding, then no current flows in the stator winding, and when no current flow in the stator winding, there is no stator magnetic field, and when there is no stator magnetic field, then there will be no armature reaction, and EA will be equal to the phase voltage V phase. Now suppose that the generator is connected to a load, and the load is normally lagging, and if generator is connected to the lagging load, then current will lag from the voltage by an angle theta, and this current is shown like this. I will draw it here like so. This is the IA maximum, which is lagging the voltage by an angle theta. Now in this figure, as the stator current is flowing in the stator winding, so this stator current produces its own magnetic field, which is denoted by BS, like this. This stator magnetic field is changing, and it links with its own winding, stator winding, and induces its own voltage in the winding, which is coincides with the stator magnetic field, and this voltage is called E stat, and it is denoted by E stat. Now there are two voltages present in the stator winding, one induced by the rotor magnetic field and other induced by its own stator magnetic field. So the voltage induced by the rotor magnetic field is the internal generated voltage EA, this one, and induced by the BS stator magnetic field is E stat. So the resultant V phase, which is found at the terminal of the stator, is EA, sum of these two voltage, plus E stator or armature reaction voltage. Similarly, the B net will be the vector sum of stator rotor magnetic field and stator magnetic field, and it can be drawn here as the vector sum. So if we add these two, it looks like this. Since BR and EA angles are same, BS and E stat angles are same, so therefore V phase and B net's angles are same. So this is B phase. Now, how the effect of armature reaction can be modeled mathematically. So in the figure you can see that this E stat is directly proportional to I max. Is directly proportional to IA. Why? If stator winding increase, as stator winding current increases, which is IA, then the stator winding magnetic field increases, and when magnetic field increases, it induces its own E stat, so E stat increases. So E stat is directly proportional to IA. So here you can see that E stat is also lagging 90 degree from EA, So it can be given as E stat is equal to minus J 90 degree IA. If X is the proportionality constant, so it can be given as minus JX IA. So that's how the armature reaction can be modeled mathematically. And as from this, you know, V phase is equal to EA plus E stat. Putting this equation of E stat here, the result will be V phase is equal to EA minus J of X IA. So the armature reaction model is modeled mathematically. So armature reaction voltage can be modeled as an inductor in series with the internal generated voltage. This can be given as EA reactance X, current flowing in it is IA, and the voltage reached at the terminal is V phase. Till now we modeled the armature reaction, which we study the first factor. This is the armature reaction, which is the first factor that causes the difference between EA and V phase. The second factor is the self-inductance or reactance of the armature coil, and the third one is the resistance of the armature coil. Now we are going to model these two factors. If the stator self-inductance is called LA and its corresponding reactance is called XA and the stator resistance is called RA, then the V phase is given by, so there just be voltage drop across the reactance of the coil and across the resistance of the coil and the armature reaction. So V phase is equal to internal generated EMF minus armature reaction minus voltage drop across reactance minus voltage drop across resistance. So this is the difference between V phase and EA. As you can see that these both are reactances. So armature reactance and self-inductance in the machine are both by armature reaction effect, and the self-inductance in the machine are both by represented by reactances, and then it is combined to a single reactance which is called as synchronous reactance. So this equation becomes more simplified and it will equal to EA minus J of XS IA minus RA IA. So this is the final equation of V phase. So that's how V phase differs from EA. Now it is possible to sketch this equation, and its sketch look like in this way. This is for one phase EA, synchronous reactance and resistance, armature resistance. For one phase, for two phase, for three phase, and this is the field winding circuit, rotor winding circuit. Rotor winding circuit, VF DC supply current, DC flow. This is the control resistance which controls the amount of the field current, and this is its on resistance and the winding on reactance. So this is the field circuit and this is the armature circuit represented like this. So it is same. Now these, as we already studied in transformer, that these three phases of the generator can also be connected in a star connection or can also be connected in a delta connection. If connected in a star connection, then you can see from figure that V terminal should be greater than V phase, and it is equal to in star. If they are Y connected or star connected, then the terminal voltage Vt is given as under root 3 V phase. But if they are delta connected, then V terminal is equal to the V phase. If they are delta connected, then Vt is equal to V phase. Till now we model the equivalent circuit of the synchronous generator. Now we are going to study the phasor diagram of a synchronous generator. As we study the phasor diagram of the transformer, also this look like almost the similar, as this is the phasor diagram of synchronous generator at unity power factor. At unity power factor, you can see Ia is in phase with the V phase. Anyhow, I am going to draw it here. Let this is the V phase arbitrarily taken at a 0 degree. I phase is in phase, Ia is in phase. So the resistive drop in the winding is given as Ia Ra, and the synchronous reactance drop, which is the minus j xs Ia. So this is the internal generated EMF EA. So that's how the phasor diagram of synchronous generator look like at a unity power factor. In case of lagging load, you can see in this figure Ia lags the V phase. So draw the figure like that. It can be clearly shown from the figure that a larger internal generated voltage EA is needed for lagging loads. Similarly, for the leading loads, we did this thing in transformer. That's why I am not going to explain it deeply. Also, book is also not going to explain these things deeply. So here Ia is leading the V phase, and when draw it, you can see the internal generated EMF is now less than the V phase. So for leading loads, for a given phase voltage and armature current, a smaller internal generated voltage E is needed for leading loads. Okay, now that's end from this lecture. Okay, thank you.